Okay, let's talk about some switches. First, before we go into switches, we're going to talk about network topology because when we talk about switches, we're also going to compare them to another network device that looks very similar, the hub, but operates fairly differently. So, when we talk about network topology, what we're really talking about is the layout of your network, how devices are connected to each other, how devices are connected to the network, etc. The most basic topology is a bus. And in a bus network, every device is connected to basically one long wire. And there's these little things called vampire taps that let you plug in, like a vampire with its two teeth, that plug into the network. And it basically just taps in, and it's an electrical signal. So you tap in with your plug, and you're connected and hooked up to the network. The beauty of the bus is that immediately, as soon as you're hooked up, you're connected to every other device that is there. The problem with the bus is that basically if any of those connections goes out, then your network could go down. So if we have a break between the laser printer and the computer that's right next to it, if that connection breaks, the entire network, the entire bus goes down and devices can't communicate to each other. Even if they have that direct connection still, like the two computers on the far left, they still can't talk to each other if it's that bus network. In a star network, we've got a central device. In this case, it's a hub. You've got a central device that is, everybody's connected to that. So rather than a wire being your device that everybody's connected to, now you have something maybe slightly smarter, a physical hardware device that things plug into. In this case, like I said, it's a hub. Everybody's connected to the hub, which is fantastic because one computer's link to the hub can go down without taking down the entire network. That one device will lose access, but everybody won't lose access if the top computer, for example, goes offline or can't connect to the network. The good thing about the hub, or the weakness maybe of a hub, is that it is still bad if the hub goes down. And that's true for most networks. There's central networking devices that, when they go down, cause problems for everybody on the network. In this case, in a star, you've got that hub, and when that hub goes down, nobody can connect to anybody anymore. Then you've got a ring. These are less common today. Still exist. In a ring network, it's very much like a bus, except that you have links between these computers instead of some central wire that everybody connects to. With the ring, you have the same issue with the bus, where if one of those connections goes down, everybody's down. Now, remember, when we talked about the data link layer, when we talked about Ethernet, we talked about the token ring protocol. That would use a ring topology. Last one we'll talk about here is a mesh. The beauty of a mesh is that everybody's connected to everybody, which means that if one device goes down, nothing happens. And this involves, or nothing happens to the rest of the network. That device goes offline, but everybody else can still communicate because you're directly connected with every other device on the network. So instead of that central device like a hub in the star network, everybody's directly connected to everybody. The problem with a mesh is that they're very expensive, because if every device is directly connected to every other device, then you have to have a network interface card or some sort of interface for every other device on your network. And it's fine if you have 4 computers on your network, but when you have 5, you had to add a whole bunch more, and 6 and 7. And for every device, your number of connections grows like crazy, and the number of network interface cards and everything that you need to make that function works, or grows like crazy. Now, this is an example of a full mesh network, and in a full mesh, every device is connected to every other device. You might also have a partial mesh where you don't quite meet that criterion, where everything's connected to everybody, but you've got a lot of different connections and redundant connections between devices that allow that network to function and function even though something might go down. So like I said, these devices look very much the same. A hub on the left, a switch on the right. I couldn't find a picture of the same brand for each, but really they're basically exactly the same. as far as what they look like on the outside. You've got some ports, some Ethernet ports to plug into, and that's it. But they're not the same device. They're very, very different. And the biggest difference is in the way that they operate. Hubs are a physical layer device, meaning, like the physical layer, they are dumb. All they are is a repeater. Essentially, when they receive a transmission on a port, they send that transmission out on every other port. So if something comes in on port 1, ports 2, 3, 4, and 5 are going to receive that transmission, and it's going to get blasted out. And that is true no matter what comes in. If you have a perfectly clear transmission, excellent. That's getting sent out to everybody. If you have a unicast that's meant for from device 1 from the device on port 1 to the device on port 3, well, great. The device on port 3 is going to get it, but also so are the devices on 2, 4, and 5. Everybody's going to get it. If you have a collision, we talked in Ethernet about collisions. If you have a collision where two devices try to transmit at the same time, and that arrives at the hub, well, guess what? That's getting transmitted out to everybody because the hub is a physical layer device. It doesn't understand anything. It doesn't know what a collision looks like. So it blasts that collision out to everybody, wasting everybody's time as each computer now has to see that collision, process it, and throw it away. So physically, a hub creates a star network because each device is connected to the hub, and yeah, I mean, that's what a star network is. But logically, at the way that it operates, the hub creates a bus network because it's essentially the same as if every device was on the same network segment or plugged into the same wire. Because it's not doing anything about collisions and it's not separating those devices at all, everybody's getting everything. So it's a physical star and it's a logical bus. A switch, on the other hand, is a data link layer device. So physical layer for the hub, data link layer, the layer 2 for the switch. It's a little bit smarter. It does a few things, a lot of things, that a hub does not. One of those things is it understands MAC addresses. Meaning, if you have a transmission from the computer on port 1 to the computer on port 3, everybody doesn't have to hear it. It can get sent from the computer on port 1, the switch sees it, says, oh, that's for port 3, sends it out, and off it goes. Nobody else needs to hear it, meaning that bandwidth isn't taken up. Those other devices don't have to process an incoming frame that's not for them. Another thing that a switch does is it drops collisions, meaning it saves a lot of bandwidth and it saves a lot of processing or network processing on each of those devices. When a collision happens, the switch throws it away. Because it's a data link layer device, right? It basically does what Ethernet does. It sees a collision, it says, okay, well, nobody needs to hear this because something went wrong, and throw it away. And the other devices can handle reliability, again, at the transport layer or the application layer if they want to. So a switch, while it looks exactly the same as a hub, or more or less the same as a hub, creates a physical star and a logical star network. So each of those devices is essentially separated from the others instead of logically being on the same network segment. So an important concept here as we talk about switches and hubs is the broadcast domain and the collision domain. Now the broadcast domain has to do with the network layer. Broadcasts at the network layer get sent out to everybody on the local network. So up at the top here, at the top of our chart here, we've got some routers. And those routers separate broadcast domains, meaning a router does not forward a broadcast. If a broadcast arrives at the router, it says, great, fantastic, but I'm not sending that out to anybody else. So inside of a router, basically on one side of a router, you have a broadcast domain. On the right here, we have a hub, and a hub also creates a collision domain. Like I said, it's like a bus, right? Where if anybody's talking, nobody can talk, nobody else can talk. And that creates the opportunity for collision. So each hub, every device connected to the same hub is on one collision domain. Meaning those devices can collide with each other. And collisions will get forwarded to every device on that network segment. Now on our switch on the left, each of those ports, each port on the switch creates a new collision domain. They're all still in the same broadcast domain because they're all on the same side of the router, and a switch doesn't do anything with the network layer. So all it does, if there's a broadcast, it's going to send that out to everybody. But each port on the switch creates a separate collision domain. And those collision domains keep collisions from spreading out to everybody on the network. So one small little corner of your network, each network segment, each port connected to your switch is a separate collision domain, and devices on those ports can't collide with each other because the switch will take care of that. So the way that the switch handles learning about MAC addresses and doing what switches do, which is separating those collision domains and forwarding traffic only to the devices, is it learns and holds on to this information about the MAC addresses that it's connected to. So as a switch receives a frame, it's going to inspect the source MAC address on that frame. And the source MAC address on that frame means something with that MAC address is on X port. So if something comes into the switch on port 1 and it has a certain source MAC address, that means that something on that with that source MAC address is on port 1, and the switch remembers that. When traffic comes in from other ports destined for that source MAC address, then it knows to send it out on port 1. And it can keep track of that stuff, keeping track of ports and what MAC addresses are assigned to each port. So there's a couple different kinds of switches. We'll talk a little bit more in just a second about the different kinds of switch capabilities. We have managed and we have unmanaged switches. That's really hard to say. Unmanaged switch. Say that 5 times fast. An unmanaged switch is, well, it means basically it does what switches do. It still does the things that switches do, learning MAC addresses and not forwarding collisions, but it doesn't have other things. It doesn't have other capabilities, some of the other capabilities that we'll talk about. Then you have a managed switch, which adds all of those other capabilities. An important thing to consider when you're looking to buy a switch, for example, is something called the backplane. The backplane. And the backplane refers to the speed of communication within the switch, or not the speed, but the bandwidth, the available bandwidth for communication within the switch. So if you have, for example, 10, or in this case, our little D-Link switch here with 8 100 megabit ports. Each device could potentially use up to 100 megabits. The device on port 1 could try to transmit at 100 megabits, the device on port 2, the device on port 3, the device on port 4, etc. However, if the backplane isn't fast enough, then you won't be able to max out all of those ports. And so when you're looking to buy a switch, if the backplane, for example, was only 200 megabits for the entire switch, that means that at most, all of the communication within that switch could be using up to 200 megabits. So even though port 1 can use up to 100 megabits and port 2 can use up to 100 megabits, if they're both using 100 megabits, then ports 3 and 4 and 5 and 6 and 7 and 8 can't communicate because they've used up all of that bandwidth on that backplane. So that's what backplane is. So what connects to a switch? Basically every network device. If you're inside of an office building, every single Ethernet jack, I tried to point to one, but I don't have one behind me. Every Ethernet jack in that building is connected to a switch. Every wireless access point needs to be connected to a switch. Switches connect to each other. So every switch is connected probably to another switch, or at least to a router. So you've got connections between the switches so devices can communicate with each other. Voice over IP phones have to connect to a switch. They connect to an Ethernet jack on the wall. So really, you've got a lot of ports on your switches. On campus, on the University of Nebraska at Omaha campus, we have, from what I've heard, about 5,000 switch ports. And inside of the Peter Kiewit Institute, where I'm at, we have about 2,300 of those. So 2,300 switch ports are inside of the building that I'm sitting in right now. And that means, that's a lot of switches. That's some pretty beefy switching equipment to store and to switch 2,300 different Ethernet ports. So switch features, speed, like I said, that's going to be important. You're probably going to be looking today at least at 1 gigabit, if not 10 gigabit switches. The number of ports, you might be able to expand the number of ports. You might start with 16 and decide that later on you need to add another 16 and get 32. So you want to look and see if you can expand the number of ports that are available to you. Or you might, if you can't expand it, then you got to buy another switch and connect the two switches to each other. Backplane, like I said, quality of service is one, and power over Ethernet. Those are two that we're going to talk about right now. Quality of service. Not everything is equal. Not all traffic is created equal. So email, whatever, right? Email gets there when it gets there. Nobody's sitting by there counting down the milliseconds until their email arrives or is sent. However, voice over IP, telephone traffic on a voice over IP network is time critical. That has to be the first thing. It has to get there when it's sent as fast as possible, and delays in the network, if at all possible, should not affect voice over IP traffic. If you've got a whole ton of people sending email, or everyone on campus is downloading Fallout 4 or whatever movie or video game they want, if everybody on campus is using that, you don't want that to affect your voice over IP traffic. So quality of service allows you to say, traffic on this port is important. Traffic on that port is less important. So you can tag each port. And again, this is in a managed switch only, not in an unmanaged. You can essentially tag each port in your switch and say, these are my important ones. These ones come first. Traffic from these goes first. The other ones can wait, and email can come later. And TCP can handle email for those later on. If we have to drop packets or anything, that can handle that. So that happens at the switching level. You can handle quality of service. The last feature, I believe, that we're going to talk about is power over Ethernet. And power over Ethernet allows us to push power through the Ethernet cable, which is amazing for wireless access points, because wireless access points have to go on the ceiling. And pretty often, you don't have a power outlet on the ceiling. So if you want power to your wireless access point, you need to be able to either run a really long extension cord down to the nearest outlet, or install an outlet up there, which is kind of a pain, or you can use a switch with power over Ethernet and run power through that Ethernet cable. So through a single port, one port, the Ethernet port, you can get all of the data and the electrical power that your access point needs. And the same is commonly used for voice over IP phones. So they only have that one jack, so they don't need to plug in power and Ethernet. They do power over Ethernet. And then also surveillance cameras are a common application for it, because they go in tiny little places, again, very often without an Ethernet jack. And so being able to run just a single cable up there is awesome. So if you need that, you need to look for a switch that has power over Ethernet and that supports the amount of power that you need depending on what devices you're going to be plugging in. A very important feature of switches is the ability to prevent switching loops. Now, remember I said switches plug into each other. And you plug switches into each other and create maybe some sort of mesh or partial mesh network. And by setting up your switches in that way, you can create redundant paths, meaning if one link goes down, there's still a way for data to get between these two switches, even if it has to go through a couple other switches. Well, when you do that, you have the potential for basically creating a broadcast storm where one device sends a broadcast, and then that switch sends it out to the other switches, and then those switches send it out to the other switches, and then those send them switches out to the others, and you basically just have an infinite loop of this broadcast getting blasted between the switches that could shut down your network. So you don't like that. Switching loops are bad. The spanning tree protocol is a method for these switches to basically talk to each other, and it shuts off a redundant link. So if we have two ways of getting between two switches, one of those is going to be shut down until we need it. If the primary link fails, then we can switch back over and open up that previously blocked link. But until we need that blocked link, the spanning tree protocol will keep it blocked so that we don't have these switching loops that cause these crazy feedback issues. And that's the end of switching. That is all you could possibly want to know about switching, but probably not. But it's a good start.